we continue our discussion on deep neural architecture and applications. In the last lecture, we have discussed about convolutional neural networks, and we have also considered different architectures of convolutional neural network. Let us consider a problem at this stage to find out the number of parameters and also to determine the sizes of the output or input to a particular layer given a specification of convolutional neural network. So, consider this exercise, a deep CNN architecture which takes an image of size 240 cross 240 cross 3 as input. So, in the input there are 3 channel input, and for the purpose of classification into 2 classes, and the architecture has 3 convolution layers, where in each layer the filter sizes are of 7 cross 7, 5 cross 5 and 3 cross 3, and the number of channels in these layers are 64, 32 and 16. So, these layers, they are specified from input to the output, and then there are 2 max pool layers in between every convolutional layer. So, which means 2 max pool layers of filter size 2 cross 2 with stride 2 in both the directions between the first and second and third convolutional layers. And after the third convolutional layers, we have 2 fully connected layers having the number of neurons as 50 and 20 respectively, and the activation function of each neuron used in this network is the ReLU or rectified linear unit function. So, the problem here is that we have to provide a schematic diagram of the architecture of the network, provide the sizes of outputs from each convolutional layers, and compute the number of parameters that you require to learn in each layer. So, let us see how we can compute all these things which have been asked here. So, let us consider the architecture, a schematic diagram of the architecture itself. So, as you can see that there is an input layer, and which is going to the first convolutional layer of filter size 7 cross 7, and since there are 64 channels, so it should be a filter size of 7 cross 7 cross 64. Then it is followed by a max pool layer of 2 cross 2 and stride is 2 there, and then again the output from the max pool layer is fed to another convolutional layers whose filter size is 5 cross 5 cross 32, because there are 32 channels output from that convolutional layer, and then again it is followed by a max pool layer of 2 cross 2 size. This is the third convolution layer or final convolution layer of our architecture. So, output from this max pool layer, it is fed to that convolution layer where filter size is of 3 cross 3, and also there are 16 channel output. So, it is 3 cross 3 cross 16, that is what we will be considering. That is not exactly filter size, it is the last 16 is showing it is the 16 channel outputs. Filter size will be 3 cross 3, we will see that thing. And then this is being fed to the fully convolutional layers where there are 50 neurons. So, the output from the 16 channel output from the third convolutional layer, they are all flattened, and they are considered as a say linear vector, and or in the one dimensional feature vector, and then that is fed to the fully connected layers of 50 neurons. This is also output from this layer also is fed to another fully connected layer of 20 neurons, and then those are again connected to output neurons. So, this is the output layer where there are 2 neurons, and it is used for the classification, because there are 2 class classification problems. So, there are 2 neurons at the output. So, this is the schematic diagram of the architecture. Let us now determine what should be the sizes of outputs from each layer. So, the input here as has been specified that it will be handling a size of 240 cross 240 cross 3. This is the input size, So, the output, if I consider 7 cross 7 filter, and as you know that it is only the output should be from those pixels of the input where this filter is fully embedded. So, filter size is 7 cross 7 cross 3, that means it is the number of channels of the input that would determine the depth of the filter, and 7 cross 7 is its width and height. So, filter size is 7 cross 7, not 64, if I have mentioned wrongly earlier. 64 is the number of channel here in this architecture, output channel. So, that 7 cross 7 cross 3 filter is embedded, and then fully embedded on those pixels, only from there the output has been provided. So, you have to leave around those boundary pixels where it is not, it could not be fully embedded. So, you have to basically subtract 6 pixels from width and height, and only one plane will be coming out of this process. So, you have 234 cross 234, and since the output has 64 channels. So, there are 64 such filters. So, the output is 234 cross 234 cross 64. So, this is the output size from the first convolution layer. Then this goes to the max pool layer of size 2 cross 2 and stride 2, which means the input size should be half of the output of max pool layer should be half of the input size, and number of channel will remain same, which is 117 cross 117 cross 64. Then it goes to the next convolution layer where the filter is a 5 cross 5, and since there are 64 channel input, so filter size would be 5 cross 5 cross 64, that is the depth of the filter. Once again you get only one plane output, one channel output from each filter. There are 32 such filters. So, you have to leave aside those boundary pixels where they are not fully embedded. So, 117 you have to subtract 4 from there. So, it would be 113 into 113 into since there are 32 channels. So, it is 113 into 113 into 32. This will again go to the next max pool layer of 2 cross 2, and there it has to be divided by 2, and since it requires full embedding of max pool layer. So, it would be only the lower ceiling or of the 113 by 2. So, it is 56 cross 56 cross 32, channel remains same. Once again 3 cross 3 cross 16 filter, that is the third convolution layer. Actually size is 3 cross 3 cross 32, and there are 16 such filters. So, you have to subtract 2 from 56, and the size will be 54 cross 50 cross 16, because there are 16 channels. Now, all these 2-dimensional array output, it will be flattened into a 1-dimensional vector of size 54 cross 54 cross 16, and that would be input to the fully connected layer of 50 neurons. So, each neuron will have that many number of weights. So, the total number of weight will be coming to the total number of weight whatever. So, output of 50 neurons from the fully connected layer would be 50 only, and then output of 20 neurons from the fully connected layer, it will be 20 only, and then you have 2 class outputs. So, there will be from there will be 2 class outputs, which is not written here, but there are again 2 outputs from this layer. So, this is the sizes of different outputs from different layers, and next we are going to count the number of parameters. So, I have indicated by arrows by showing that we will be counting the parameters of those layers which is associated with those layers. So, consider the first layer. So, we will be considering number of parameters. Consider the first convolution layer, as the filter size is 7 cross 7 cross 3, because input is 3 channel. So, the one filter size would be 7 cross 7 cross 3, but there are 64 such filters. So, it would be 64 cross 7 cross 7 cross 3, that many number of weights, and each 64 filters will have also bias. So, plus 64 bias. So, in the green color I am showing this count of parameters. So, this is the answer, that the number of parameters in the first convolution layers will be this. Similarly, for the max pool layer, since we know that max pool layer it does not require any weight it is already specified by its sizes itself. So, the number of parameters would be 0 there. So, that is what is max full layer. Next layer 5 cross 5 cross, then the filter size is 64, 5 cross 5 cross 64, depth is 64, and how many filters are there? There are 32. So, it should be 5 cross 64 cross 32, that many weights, plus there are 32 filters. So, there are 32 bias. So, this should be the number of parameters from this layer. Again there is a max full layer. So, we will have 0 here. In the next it will be fed to the 3 cross 3 filters, and depth would be 32 because the input to that layer, it has 32 channels. So, it is 3 cross 3 cross 32, and there are 16 filters. So, 3 cross 32 cross 16, plus for each 16 filters there are 16 biases. So, we will have 3 cross 32 cross 16 plus 16. Next it goes to the fully connected layer, and as I mentioned that the size of the input here is 54 cross 54 cross 16. Each input will have a weight to the fully connected layer, and there will be 50 such neurons. So, there will be 50 such bias. So, it should be 50 into 54 cross 54 cross 16 plus 50. So, that is what here, and here the size is 50. So, it will be 50 weights should be connected to every neuron of 20 neurons, and there are 20 biases. So, it is 50 cross 20 plus 20, and again since there are still you require more weights because this is the output layer. So, output here its size is 20. So, each neuron will have 20 weights and 1 bias. So, it should be 20 cross 2 plus 2. So, this is the total number of parameters those are involved in this architecture what I have specified in the problem statement. Understand that this is how that parameters and sizes could be determined given the specifications of a particular CNN. So, let us now consider another kind of problem which can be solved once again using convolutional neural network. This problem is called object recognition and localization. So, in this problem the task here is that given an image, not only you have to identify the level of the object, but also you have to identify the portion of the image where this object lies in the form of a rectangular block. So, any rectangular block can be defined by the 2 corners of the block in pixel coordinates. So, that is how the specification of rectangular block will be there. So, there are different techniques. This is a very classical problem, and even before the deep neural architecture there are methods by which people have tried to solve it. So, it is a pre-CNN, and the fact is that the object where it is the region of the object in the image that needs to be identified, and we call that task is as a region proposal, and which means you would like to find out a probable region which contains an object, and then you try to find out that what is the object in that region. So, this is a kind of approach. So, so there are stages, like first you propose a region, and then you describe that region by features. So, you have to extract features and then use those features to classify, and if you could find some objects in your target in your classes, then you decide about that. Otherwise, you may say that region does not contain any object. So, there are various methods which have been reported. So, one method was very exhaustive, means you are searching every rectangular type of rectangular block, which is a combinatorially hard problem. You need to use some heuristics there. So, so that is what I mean, you should do it, and there are methods also to propose use certain heuristics to propose those regions. And then for feature extraction you can use some handcrafted features. Handcrafted features, I mentioned what is used considered as handcrafted features. By considering the classes of objects, you predetermine that what kind of features you will be computing. For example, you can use shift operator, you can use the descriptor of shape, or other kind of key point detectors and key point descriptors. Those, and then combine them, aggregate them to define a feature. And then there are different classification algorithms you can use, like linear classification algorithms. For deep neural architecture based technique, there are 3 such variations. So, very first a technique called RCNN has been proposed. So, RCNN, what it does, it considers the task of region proposal should come from the conventional methods, and then the feature extraction part is only should be done using CNN. So, that no, you do not have to use any handcrafted design. So, as per your problem, features could be extracted, learned and extracted, and then use a classifier to find out the object. For example, linear SVM, that is a classical classification classifier. Rather another improvement or variations over on top of RCNN, where the both feature extraction and classification is done by a deep neural network, whereas the region proposal is still carried out using the conventional methods. And the third variation, that whole thing can be performed, can be done using a deep neural architecture. So, this diagram, it is explaining this flow of this computation. So, you have an input image, and then the regions are proposed. So, these yellow boxes are proposed regions by conventional methods. Then you extract them one by one, and then feed it to the CNN. As CNN takes a fixed input size, so you need to warp those regions and then compute the features. So, last layer of the CNN will give you a feature descriptor, and which is used in a classifier. Once again, this classifier is a conventional classifier, and then you decide what kind of class it is based on those target classes of this classifier. For this particular method, as I mentioned, that it uses conventional method for proposing regions. So, there is a method based on selective search, which uses hierarchical grouping based on color, texture, size, and it is a bottom up method. So, it performs bottom up segmentation, then it merges regions at multiple scales, and then based on the regions property, it decides whether it contains any object or not. So, this figure tries to summarize this process. So, it considers very small segments at the bottom layer, then it merges it and the bigger segments, and it tries to identify out of them, some of them are considered that they contain the object, and then you use the rectangular box enclosing those particular segments. Their problem in this method is that the training objectives are not very clearly mentioned here. As you can see that the CNN is a feature extractor stage, but no, what should be the objective function of that CNN? So far we have discussed about training of CNN based on some classification task. So, even the features are learned based on the end objective of classification, but in this case, since the classifier is a conventional classifier, the classifier is independently designed. So, this is a problem. So, you have to consider some intermediate objectives to learn the CNN. So, kind of ad hocism is there. So, you can use some pre-trained network, but again you need to do fine tuning based on your domain, based on your problem domain. So, that is required, and also you require to once again train the SVMs, support vector machines, based on those features, and usually feature descriptors are quite large. So, this will take a lot of time. So, and also another training you have to do, because you have to find out the regions. So, though the regions are proposed, but you need to do some kind of fine tuning. So, some kind of regressions based on those proposed regions you need to do. So, that also requires some training. So, there are so many different kinds of trainings are involved. That is why it is very slow, and also it takes a lot of disk space. So, inference is also slow. It need to run full forward process of CNN for each region proposal. So, that is what, because for each region proposal you are extracting features independently, and you will need so many times you need to iterate this process. So, that is why its inference time is very large. It is quite it takes quite a bit of time. So, what are the times components here? You can see there is a time called prop time or proposal time. So, it is time taken for generating all proposals. Then number of, depending upon number of proposals that is generated at this stage. So, each proposal has to each region has to be fed to the CNN so that it extracts the feature. So, it is number of proposals into the time taken for computing features using CNN. And finally, each one once again has to be classified. So, there is a classification time and time taken to identify the object in the image. So, this is the total inference time if I consider for RCNN. So, to an improvement over this particular approach is that now we can use a fast RCNN network, and here the idea is that instead of using an SVM, we can use also the whole thing, classification and feature extraction can be carried out at the same go. That means, for every region it will be passing through both feature extraction and classification in this case. So, it computes CNN feature map for the whole image. So, and also it is not required to compute the feature map of the whole image. You can just process the feature maps in the ROIs, and here only the thing is that it pulls the ROIs, and then again it passes to the classification stage. So, it is not that the deep neural network deep architecture is not there at the classification stage, it is a conventional classification. So, this is what it is doing. It only uses the same convolutional neural network. So, given the image, it computes the whole feature set, then using the region proposal it pulls those features and use a classifier to compute to classify it and also the objects. So, the time here is the proposal time, it remains proposal time, and then since it is only computing one time all the features, it is only one time convolution network is used. So, it is 1 into that time, but no, every region, every proposal is separately classified. So, it is number of proposals into FC time. So, first RCNN, the features are that each feature vector to sequence a fully connected layers and 2 sibling output layers. So, a layer with the softmax probability estimates over k object classes plus a catch-all background class. So, you are considering that, and another layer producing 4 real valued number for each of the k object classes. This is actually regression of the regions. So, it just shows the architectures of RCNN. You can see that every proposed region is passed through separately through the convolution layers, and then those are used for classifying and regression of the regions using regression module and also the SVMs for classifications. Every regions are processed in this way. Whereas in fast RCNN, you have the only one time the convolutional neural network is used to generate all the features, and also it has proposed the regions. So, use those regions in the feature map, those are used for classification. So, those are fed again to the fully connected layers, and then so it is a classifier which could be also neural network classifier like ANN classifier, and those are used for classifying the object and also the finding out the regions. That means, fine tuning of estimates of the regions using a regression box. The loss what is used in the stages, classification stage, as I have shown, where there is a fully connected layer which is simultaneously classifying the object and also detecting the box or rectangular area where the object is contained. So, there are 2 components of this loss. So, one component is due to classification and the other component is due to the regression. So, and we are only considering those samples, those classes which are object classes. So, U is the ground truth, P is the predicted class. So, if only it is a object class, then only we are considering the loss due to the regression, and this is a linear combination, lambda is any parameter. So, this is the thing, this is the log loss, which is cross entropy loss. This is predicted class scores, P is the predicted class scores, and U is the true class scores, and this is the smooth L1 loss. L1 is the function which is used for computing the regression, the box, the error deviation of the localizations or deviation of the rectangles from the true rectangle to the predicted rectangle. So, TU is the true box coordinates and V is the predicted box coordinates. So, this is how the loss function is defined. So, then improvement over even fast RCNN is faster RCNN, where the whole task has been considered doing it in a convolutional network. Even the region proposal also is done using a convolutional network. So, we call it as a region proposal network. So, what we can do that using the features what is generated by the convolutional layers, the same features are used for generating region proposals, and from the region proposals you pull those features which are there in that proposed region and used it for classification. So, that is why it becomes so fast, and you can see that the first stage is that you generate a feature map. So, use this feature map to propose regions and also use this feature map to classify and also regress the rectangular boxes. So, this is what is faster RCNN, and in the region proposal network the task is that we can slide a small window on the feature map, and then we can build a small network for classifying object or non-object. So, here the task is that you have to classify the object or non-object and also regress the bounding box locations, and this initial this is the initial localization. So, these positions are used, and final localization is considered at the final stage of classification and regression, where box regression performs final localization. So, and the faster RCNN, as you can see that it requires only there is no proposal time separately, it is one time convolutional time and then number of proposals into the time required for classification. So, this is describing the region proposal network. So, you take a sliding window in the feature map and it is a 256 dimensional feature descriptor, then you are classifying as object or non-object or regressing the box locations. So, this will give you the initial box locations of the object. Again in the last stage, when you are classifying the objects, you can make a fine tune of that locations. So, for region proposal network loss, what it considers that in this sliding window there are different shapes of windows are also considered which may contain a box object. So, there are k anchor boxes. So, each one is tested whether it contains a object and also this box itself becomes the coordinates, those are output of this region. So, it contains there are two components, one is once again classification loss, once again it is a regression loss. So, these two components are used in the loss function. In the two class loss function, standard cross entropy loss is used, and because you are deciding whether it contains object or not. So, if your predicted object is intersecting about 0.7 of the true object, 7 area, 70% of the true object, then we call this is 1, otherwise it is 0. So, it is intersection of union. So, this is the ratio of intersection of predicted object and predicted region and true region divided by union of predicted region and true region. So, if this ratio is more than 7.7, then we call it is 1. If it is less than 0.3, it is 0, and otherwise it do not contribute to loss. So, with this let me take a break here, and we will continue this discussion in the next lecture. Thank you very much for listening it.